Hey everyone. Well, so I wanted to talk about logistic curves. I want that to be in focus. Okay. And so what I want to say about logistic curves is that we know that the rate of change in the amount any population you want, I don't care, in the amount with respect to time is proportional to both the amount is proportional to the amount. There we go. I want to say the amount used or the amount already there. Amount present and how much more there can be. I know that's vague. It'll become clear briefly. Yeah, no, really will. So what we're thinking about here then is the rate of the change in the amount, proportional with respect to time. There's rate of change in the amount with respect to time is proportional. Now, both. That means instead of having Ka, I've got Ka times how much more there can be, L minus A. L, that's the total amount possible. Okay, so this is a different kind of differential equation. This derives our PERT model. This was the Wolf's model. And what happens when we put these two together is PERT Wolf's y equals L. We get a logistic curve. So how does this turn into our logistic curve equation? Funny you should ask. I'd like to derive that for you. No, this is not Honors AP Calc. You will not have to derive this. Just sit back and watch the show. You know, I guess what I want to say is follow along and marvel at it. Because a human figured this out probably before we had indoor toilets. I know. Here we go. We're saying that dy dt equals ky L minus y. Okay, we want to solve this differential equation. Fabulous, no problem. Separation of variables. I got you, Kukla. Here we go. Y L minus y equals k dt. Sure, and we integrate. Nice. And over here, sure, kt plus c. What the hell is that? Do you recognize it? Okay, well, guess what? This is partial fraction decomposition, right? I've got these two factors. So 1 over y, L minus y, case 1, a over y plus b over L minus y. Okay. Multiply everywhere by the least common denominator. 1 equals a L minus y plus by. Now, I'd like to solve this system. And, I have two magic numbers. Y equals 0. So if I plug y equals 0 in, this goes away, and I get that a times L is 1. And so I know that a is going to be 1 over L. Now, that was one magic number. Well, the other magic number is if y equals L. If y equals L, L minus L is 0, and 0 times a, that goes away, but we put an L in here. So we have 1 equals BL. And therefore, B also equals 1 over L. Nice? Okay. So now we're ready to go back to here and say that A is 1 over L and B is 1 over L. L is a number. L is a number. These are variables. L is a number. Okay, now how does this help me? Well, I'm going to now take this thing, and instead of writing it like this, I'm going to say, well, I can write that as the integral 1 over L of y plus 1 over L minus y dy. And guess what? This is why we needed to learn partial fraction decomposition. I can't do this problem without splitting this up, without coming to this. Now, I will say that many of you will be comfortable pulling that constant out. Okay, so I'll pull that constant out. I'm going to have 1 over L integral 1 over y plus 1 over L minus y dy. I actually strongly encourage you to be careful and pay attention right now. This is kt plus c. Okay. So, yeah, I need to split this into 2. And if I don't deal with this now, when we split this into 2, people are going to forget this going to that second one. So, before we integrate here, let's multiply both sides by L. So I'm going to have the integral of 1 over y plus the integral 1 over L minus y dy equals, I'm multiplying both sides by L, LKT. And look, that's a constant times some number. Nobody's going to freaking know, so just let it go. Now about this is another place where people have difficulty, and I strongly recommend that you do this kind of thing. LKT plus C. So that's ln of y. Now, what's the antiderivative here? Were you going to say it's the ln of L minus y? Well, 1 second on that. So if I took the derivative of this, ln of stuff, well, I'd have 1 over stuff. Don't I have to come back and take the derivative of the inside function? The derivative of minus y would be -1. I don't see that -1 anywhere here. So there must have been something present on the original function, so that when you took this derivative and that -1 suddenly popped out, -1 times negative, turn that into that positive. Right. LKT plus C. Fabulous. Now you know what I'm going to do? I'm going to use my log properties from Algebra 2 to say 2 logs joined with minus means I can combine them into 1 log with division. And now exponentiate. And so we're going to get y, L minus y, equals, what do we have here? E to the C times e to the LKT. I did have a an absolute value over here, so I do need that plus and minus. Yeah, that should be, this will make sense for you. There. So when I do this, I have this, and when I want to take those off, I need that. So let's say that plus and minus e to the c is b. So I've got y, l minus y, b, e to the l, k, t. Oh, wait a second. I suddenly feel queasy. Do I feel queasy? I think I feel queasy. Let me think about this for a minute. Yeah. So here's the thing. You know, sometimes it's sort of amazing how much you have forgotten about your life that other people remember about your life. Like, do you remember your first steps? No. Do your parents? Probably. They have a good chance of remembering what your first word was, not only when you took your first step, but where it was. You don't remember any of these things. Your body protects you from all this trauma by letting you forget them. Yeah, well, I just walked into a big old nightmare. You know, I did this problem one year, and I did this. Wow. I got a note here in my notes, which I haven't been following, and it's pretty clear because I just sort of ran into it here. Yeah, I got some PTSD about this. This is really like, my brain really wanted me to forget it. But luckily, I made a note to myself that if you go down this path further, it says here, tears of small child. So let's back it up a step or two. And let's see where we were. We had ln of y, and we had minus ln l minus y, and we had lkt plus c. We were there not long ago. Yeah, so now I have to actually do something completely unintuitive. And I don't just mean unintuitive for you, but Mister, I've been teaching calculus as long as you've been alive, even though I failed it twice in high school. Still not intuitive for me. Because what I'm going to do right now is I'm going to factor in negative 1 out of both of these. And when I do that, I'm going to have negative ln of y plus ln l minus y. And you might be saying, why would you want to do that? Tears of a small child if you don't. And on the other side, I still have lkt plus c. Well, this negative, yeah, I don't want it on this side anymore. I want to move it over here. So I have minus lkt. I know, it seems like, cuckoo, why? That's so stupid. Try the other way. Try the other way. Just finish that one. And you'll know why it is that I wanted to flip these. I want the minus here and the plus here. Because when I condense these into one log, now what I've got is L minus y over y equals minus lkt plus c. I exponentiate. Cool, those go away. I'm going to rewrite this as e to the c times e to the minus lkt. I'm going to take these off and do that plus minus thing. And yes, I'm going to say plus and minus e to the c is equal to b. And so now I can write L minus y over y equals b e to the minus l k t. Cool, but we're not done. Because remember, this needs to say y equals, and it doesn't yet say y equals. And Noah said at this moment, he said, Mr. Kukla, there's no numbers. There's no numbers, Mr. Kukla, and you're still talking, and you're not done, and there's no numbers. And there's not. There is, though, Kukla multiplying both sides by y. L minus y equals y, b e to the minus l k t. Yeah, not done yet. Add y to both sides. L equals y plus y b e to the minus l k t. Okay, and then, well, I don't want L equals, I want Y equals. Well, look, two terms and they both have a Y. Let's factor a Y out. Y divided by Y is not 0, but 1. And I took this Y out, so I have B e to the minus L k t. And what am I solving for? Y, which means I have to divide both sides by. Don't lose the B. L k t. So finally, I'm done, and y equals L over 1 plus b e to the minus L k t. Normally, you don't see this. You just see some constant here. But we know it's L k t. Yeah. Wow. That's a lot going on. By the way, partial fraction decomposition is not a Calc AB topic. It is at best a BC topic. It is something that is on the Calc 2 curriculum. Integrals with partial fraction decomposition, not in our class, in your next class. You will be deriving things like that. In your next class, you will need to do partial fraction decomposition. So, what do I want you to do with this? Well, I want to look briefly at the in-class problems. And the in-class problems are going to be this worksheet called Applications of Differential Equations, Exponential and Logistic. So, what we've got here is a bunch of problems. And I want you, so that you're ready to actually do this when you get to class, I want you to look at these different problems and tell me which model we're going to be using and whether we have to derive it or not. Now look, anything that's logistic, don't worry about it. You don't have to derive it this year. I don't recommend you derive it this year. This is something for next year. But I do think you need to be able to work with that logistic equation that we just came up with. All right, so let's look at these. Easter Bunny has begun to express his malevolent side. This year, instead of hiding real eggs, he's hiding eggs made of a radioactive substance, NB95, which has a half-life of 35 days. If the danger eggs have a mass of 2 kilograms, and you don't find the one hiding under your bed, how long will it take for these eggs to decay to harmless, which is 50 grams? Okay, so I don't want to do the problem now. I just want you to tell me what model will you be using, and I want you to tell me if you have to derive that model here. What do you think? Well, it's an exponential decay problem. We know it's an exponential decay problem. We've got a half-life. So, I could understand you saying, well, Mr. Dupuy, you told me how much I started with. I started with 2,000 grams, and I know the half-life shortcut, where K is L1/2 over time for half-life. So, can't I use this? And the answer is, well, do they explicitly give me a rate here? I'm not expecting you to derive this one. Okay. I feel like the last couple of videos, has been deriving one. Likewise, this one. Radioactive isotope has half-life of 16 days. You want to have 30 grams after 30 days. How many grams should you start with? Well, again, this is going to be this is exponential decay. I just feel like that's so powerful. That's, just say jump on me. Let's see what would it look like, because I don't think I've recommended this. Let's see what it would look like if we started with the rate of change in the amount of stuff with respect to time is proportional to the amount of stuff we have. Okay? So RK, let's not do that. So we've got A over A equals K dt, and we integrate A equals K t plus C. We exponentiate absolute A equals e to the C, e to the kt. So A equals plus or minus e to the C, e to the kt. And we can say plus or minus e to the C equals a sub O. So I get A equals a sub O e to kt. Well, that wasn't so bad. And now we plug our K in there. They didn't give me the rate. I don't know. What does Mr. Paz do? Mr. Paz, don't worry. This is not the sort of thing we need to worry about on the AP exam. On the AP exam, we will know. We will know if they give me that rate, I must integrate. Otherwise, okay, what about this one? The third question. Third question here, highly contagious pink eye has been ravaging school. The population in school, 1440. Including students and staff. Rate of infection proportional to both the number of students infected and the number of students not yet infected. Both. All caps, both. Which model? Which model is both? Well, both is logistic. So I'm using logistic here. Now, to think about this for a moment, now I'm going to do the problem. I'm going to say that L, the carrying capacity, is 1440. And I'm going to say that the rate of change in the number of students infected with respect to time is proportional to the number of kids infected and how many more kids can be infected. Okay? So, this is the number of kids who've already been infected. This is the number of more kids who can be infected. Right? Total number infected can't go above 1440. There's only 1440. So, if S of them have already been infected, and we can only have a total of 1440, then 1440 minus the kids who are already infected. These are the kids who are not yet infected. And these are the kids who are infected. And so look, the rate of change in the number of students who are infected is proportional to how many are infected and how many are not yet infected. I stopped there for a moment, not because I didn't want to look at more of these concepts, but instead because I was thinking about, do you remember back in August we said that with this logistic curve, we're always increasing, but there's this place here where the rate, where the infections are increasing fastest. And then we understood that this was an inflection point. But in August, we said that this is our carrying capacity. This is our L value. And in August, we said that this number, the Y value of this number, was L over 2. And I kind of want to say, I think you should actually prove this. I think you should prove this. So, if we have a logistic model, like the one we derived, was it L1 plus B e to the minus LKT, so you just do that right there. I'm going to go with LKT. So, prove that this has an inflection point whose value is L over 2. Yeah, Mr. Pause, you should have them do that. As extra credit. How about that? Yeah. Yeah, do this problem as extra credit. Here's your logistic curve. Here's what we knew in August before we did calculus. This inflection point happened today when y was equal to. This is a y value. This is not a t value. This is y equals L over 2. Don't plug L over 2 in there and solve. No, I'm asking you to do something different. I'm asking you to prove that this function has an inflection point when y equals L over 2. Okay? Okay. So, enjoy. That'll be fun. Yeah, I think it is. Okay. U-235 is an unstable isotope of U-238. Both are found, by the way, in the Southwest. Many uranium mines in the United States are located in Arizona. I know. And both are used in nuclear weapons. The half-life of uranium-235, the unstable isotope of 238, is 710 years. And the warhead from the Minuteman W62 warhead is 235 pounds. Create a model that tells us how many pounds of 235 will we have left after 2 years. Well, this is just exponential decay. This is just a half-life problem, so don't be scared about that. Now, what about the back of this worksheet, which for you will just be another round or breakout room problem, depending on what Mr. Paz does. Sarah likes mollies above all other tropical fish. This is not a drug reference, please. Get your head out of the gutter. This is the tropical fish. Go look at the tropical fish. Her fish must really like each other because they're reproducing like crazy. The rate of increase in the fish population is proportional to the current population of mollies and the number of additional fish the tank can support. So what type of molly is that? Is that PERT? No. How do I know? Because the rate of increase in population is proportional to both. Two things. Proportional to two things. I know that's logistic. Okay, for what value y is the rate of change greatest in the logistic model? Oh. Look, here we are proving it. Never mind, it's not extra credit. You need to justify that. Oh. Mr. Paz, have them do this. Have them do this, Mr. Paz. Don't worry, he's not going to watch this. You're safe. Okay. Human zygote consists of one cell at conception. The number of cells grow to 8 by the end of 1 week. Assuming the rate of increase is proportional to the number of cells, how many will it take for us to get 100? Well, look. Assuming that the rate of increase is proportional to the number of cells, yeah, 1, this is PERT, and 2, yes, I have to derive this. They've given me that equation. I mean, they told me the differential equation. When I look over here, I was not given the differential equation. Here I'm given the differential equation, not given the differential equation. When they give me those words for the differential equation, assuming the rate of increase is proportional to the number of cells, how many weeks? Yeah, you need to derive this. So you need to derive that. Newton's law of cooling, well, Calc 2, sure, derive that. Honors AP Calc, sure, derive that. Us, no, just work with the formula. The rate of change in the population of Irukandji jellyfish off the coast of Australia is directly proportional to 450 minus p. And by the way, this is 450,000. I know, I didn't want to write 450,000, but just be mindful of that. Current population times t in years if, proportional to 450 minus p. This I have to derive. Is it going to be PERT? No. This is the wolves problem again. This is the wolves problem. So think about solving this differential equation. If you get stuck, think about the wolves problem. Okay, and number 10, real estate developer opens up subdivision, 120 plots. She builds 5 homes and then opens up a laptop with builders. The number of homes built starts slowly, increases faster, and then slowly peters out as the last lots are built on. The rate of change in the number of homes is proportional to the number of homes as well as the number of lots remaining. This is logistic, right? Starts slowly, gets very fast, and then peters out. 120. We approach the total number of lots sold. And then here too, what did they say? They said the change in the number of lots with respect to time is proportional both to the number of lots and how many you can still have. This is logistic. Don't derive this unless that's your definition of fun. I would recommend instead that you spend the time thinking about what the hell you're supposed to do with the 70%. All right, bighorn sheep. Bighorn sheep in the mountains around Tucson, their rate of change in population is proportional to 100 minus p. That's the wolves' problem again. And a plan to increase the population by studying interactions and helping carve out transit routes. Oh, this is just a continuation of 11. And that's all we've got. So, there were only a couple of problems there that you actually have to derive. You should do those, because solving those differential equations are really, I think, the stuff you should do. All right. So, now I kind of want to say if you've gotten through this, that's pretty good to being done. I'd like to do 3 more problems with you. I kind of want to do a 4th one, but I don't know. These are just practice on the stuff that we've done already. And let's take a look at our logistic model. If I'm not supposed to derive it, how do I use it? Okay. Obese America. So, I'm going to tell you that you can't have an infinite number of obese Americans. There is a carrying capacity. There's a maximum number. You can't have more than all the Americans. So, in 2014, the population of the United States, 318 million. Okay. We're going to be using dy dt equals ky L minus 1. Okay. Now, we've solved this, and we know that y is equal to L over 1 plus b e to the minus L k t. Okay? So, let's now use this model. Oh, I guess I need to give you some more information because we've got a bunch of letters to solve for. So, this is this is not t equals 0. T equals 0 is 2008. In 2008, I was able to find that there were 103.36 million obese Americans. That's right, 12 years ago, a third of the Americans were obese. And by the way, this number includes all the babies and all the children. A third of the Americans were obese in 2008. 2 years later, the number was 109.956. So in 2010, we have even more obese Americans. Okay, so this is our initial information, and I'd like to build our country's obesity model. All right, we know the total number of Americans. So I'm going to plug in 318 here, and I'm going to plug a 318 in here. Minus 318. Now, what about plugging in this? So I've got the order here 0, 103.36. That's a time, and that's a y value. So 103.36 equals 318 over 1 plus b e to the, if I plug in the 0 there, this is all going to become 0. And so what do I have? E to the 0 is 1, so I just have 1 plus b. Okay, solve the equation for b. Multiply both sides by 1 plus b. 1 plus b. Sorry, that's over here. So we have 318, right side, and here, 1 plus b. There we go. Now, resist the temptation to distribute. Trust me, it's a lot easier just to divide both sides by 1 and 3. 1 through 6. Now, that's going to be b plus 1. So I'm going to take this number and subtract 1, and that'll be my b value. So what's my b value? 318 divided by 103.32 is 3.0778016,492. But that's 1 plus b. So I need to subtract 1 from that. And I end up with b equals 2.077816492. So I got my b value. Goes in there. Nice. Okay. This goes in. All right. Well, we've used this up. So now I've got y equals 318. 1 plus 2.077816492 e to the minus 318 at. All right, so we have this second order pair. I'm going to plug a 2 in here, and I'm going to plug a 109.956 in here. 109.956 equals 318 over 1 plus 2.077816492 e to the minus, we were plugging a 2 in for time, so 2 times this is negative 636. Okay. All right. Multiply both sides by this denominator, so it cancels here, and I'm going to multiply it. But, again, resist the temptation to distribute. 1 times 1 plus 2.077816492 e to the minus 636. Okay. Equals 318. All right. Now, the reason I don't want you to distribute is because I want you to divide. And then I'll subtract 1, and then I'll divide by my b value, and then I'll take the ln of both sides, and then I'll divide by negative 636. Okay, so 318 divided by this number, 109.956, and I get 2.892. I need to subtract 1 from that. Now I need to divide by my b value. So I'm going to divide by 2.077816492. And I'm going to get that e to the minus 636k equals 0.9126029934. So to get this down, I need to take the ln of both sides. And then I'm going to have to divide by that negative 636. So I want ln of the answer. Divide that by negative 636. And finally, I have my k value. This k value that I've been looking for is really tiny. Look, it even says e to the minus 4. Well, don't forget our model looks like this. This is our model, and we're plugging this k in times this number. So I'm going to multiply this k value times this. So times negative 3.8. All right, so now I can finally write y equals 318, 1 plus 2.077816492 e raised to this number, negative 0.046824134 t. Hot dog. That's our obese American model. Remember, t equals 0 is 2008. Okay? So, What do you want to know? Do you want to know how many people are obese this year? How many years after this are we in now? Well, 13. So if I plug a 13 in here, I'll know how many obese Americans there are. But the problem that I actually want you to answer is, if this is the obese American model, and oh, by the way, there's lots of advertising, there's government money spent on telling you not to be obese and to eat healthy foods. And there's a lot more money out there from the makers of chips and ice cream and other things like that, who would really like you to continue to buy their product. So, I want to ask the question, when will all adult Americans be obese? So, I looked this up, and this 318 contains all the kids, all the infants, and when I looked into what percent would be adults, yeah, so when y equals 240, that would be all the adult Americans based on this. Now, I understand that as time goes by, this number gets bigger. So just human. Based on 2008, when would all of the adults, according to this model, be obese? 40. Let's solve that equation for 2. Now, I'm not going to ruin the surprise for you. You need to find out when this is going to happen. And if you don't think it's ever going to happen to you, look again at those kids who used to be seniors at Sabino 2 years ago, when you were a sophomore. Yeah, go see what they look like. They put on some weight, by the way, going to college. Yeah, that's where it starts. And then it's called baby number 1, baby number 2. No, I'm not talking about birth weight. I'm talking about all the stress that having those kids causes in your life. Oh yeah, 10 of my extra pounds were definitely son number 2. Maybe 20 pounds for the first one. Oh yeah. Watch out. Watch out, watch out, watch out. Okay. Dead body number 2. Detective finds the body at 9 a.m. The body's temperature was 90.35 degrees Fahrenheit. The room temperature is 68 degrees Fahrenheit. At 10 a.m., the body's temperature is checked. Now, that's 1 hour later. So, if we say the detective found them at time equal to 0, the temperature was 90.53 degrees. And at 10 o'clock, the temperature was checked again, and this time we have 89 degrees. Okay, so we've got these two little pairs. Determine the time of death. Good. So, not deriving Newton's law, just saying, here's Newton's law. E to the t. Yeah, it doesn't matter if there's a minus there or not, because this is a number. And when I plug stuff in, I'm going to get a number. All right, I'll put the minus. Oh, but really, I don't need to have that minus there. All right, so what do we know? Well, we know temperature of the surroundings. 68, 68. At time equals 0, what was the temperature? Ooh, 90.3. Great. So I filled in a lot of stuff. This is my input variable. This is my output variable. All I have to do is solve for this, and that's why they've given me that. Great. I'm going to figure out what that is. 98.3 minus 68. That's 22.3. So T equals 68 plus 22.3 e to the equation 2. Okay. 90.3 plus was and 68. Good. Okay. Plug in this order here. 89 equals 68 would be 1 times K. Please don't combine this. This does not have an e to the k attached to it. This does. You cannot combine this. But you can subtract. Subtract 68 from both sides. Divide both sides by 22.3. And take the ln. That's going to give us our k value. Okay, so now I have a k value. ln of 21 over 23 is our k value times 2. Cool. Now we've got this model. Well, what are we going to do with this? Well, remember, we were asked to find out when did this person die. That's what we're trying to find out. When did this person die? Okay, well, when they died, what do you think their temperature was? Now, if there was a big scuffle and their temperature elevated, this isn't accurate, but this is a ballpark. You know, I was expecting on average the temperature should be 98.6. 68 plus 22.3 e to ln of 21, 22.3 t. And I want to solve this equation. So I'm going to subtract 68, divide by 22.3, and take the ln of both sides, and I'm going to divide by this. So, what do I get? 98.6 minus 68. 30.6. I'm going to divide by 22.3. I get 1.372197. That's what I need to take the ln. Taking the ln of that number. And I get 0.3164133305. Fabulous. So 0.36413305 equals ln of 21 over 22. Well, this is just some number. So I'm going to divide both sides by that number. Divide by ln of 21 divided by 22.3. And I end up with t equals negative 5.268 hours. What does that mean in the context of this problem? It means that if time equal to 0, the body at this temperature, that 5.268 hours ago, the body had a temperature of 98.6. When did the detective find the body? What was time equal to 0? That was 9 a.m. If we go back 5 hours, now we're at 4 a.m. It's a little earlier than that. 0.268 times 60. That's going to be 16 minutes before 4 a.m. So 3:44. We think it's 3:43 and some number of seconds, but I think that's pretty good. A.M. Fabulous. You won't get this kind of answer in the real world because there are lots of other variables here, right? Like, what if the temperature of the surroundings was not constant? What if the temperature of the body when it died was not 98.6? This just gives us a ballpark. Sometime before 4 a.m., this person was killed. Be very sad. Okay. Yeah, I would strongly encourage you to ask Mr. Bonds to do number 53 from the textbook. 53 from the textbook. I think that would be a good use of some class time. Wow, I have filled 2 sides of paper with that. And that's why you want me to do that for you. Do we need another Newton's law of cooling? I don't know. Maybe. You know, I will say that that this actually happened to my mom recently. Not this year, but last year. Yeah, my mom lives on Cape Cod, and sometimes the winters there are tough. And there was a big storm last December. Power went out at 1 p.m. And the funny thing about the power going out at 1 p.m., yeah, so not only does she not have the internet and lights at 1 p.m., but the heater, gas burner in her house is running with electricity. And so, when there's no electricity, there's no heat. And this is winter. So, when the power goes out, the temperature was 68 degrees. That's our original temperature. Okay? And at 10 p.m., when you think, I think I'm just going to crawl into bed because, my candles have run out because there's no electricity. So there's no lights. So I go to bed at 10 p.m. and notice that the temperature is 57 degrees. How many hours later is that? It's 9 hours later. So that's T7, 9. If you prefer, 9, 57. And this would be 0, 68. Now, what my mom was concerned about, she called me before she went to bed, she said, outside temperature is 10 degrees Fahrenheit. Now, what she's really worried about is if she goes to bed, when she wakes up, and she usually wakes up around 7 a.m., will the pipes be frozen? So here's the thing that we don't have. We don't have to worry about pipes freezing where we live very much. But back east, the thing is, if the pipes freeze, when things get warm, there's expansion. And that frozen water in the pipe expands past the diameter of the pipe. And so your pipes burst. Oh my goodness. In 2016, my dad was in the hospital, and his sister was there to sort of look after him. And things went really bad for him. I mean, he was in the rehab place, and they over-medicated him. And then suddenly, he was in the ER for a week. And that was really scary. My aunt said, I can't stay here any longer. I have to go back to work. And so what she did was she left the faucets running in the bathroom upstairs and in the kitchen downstairs. And she said, at least we don't have to worry about frozen pipes. And this is in January. Well, my dad almost died. And he didn't. And the nice people in the emergency room kept him alive. And then he went to a different rehab place to get better. And I came to visit him. Now, there was nothing I was going to be able to do to fix anything. So I didn't rush over there. I waited until rodeo break. And when I got there for rodeo break, I heard a really interesting noise when I walked into the house. It sounded like a river. And it was. The floor on the first floor was like an inch of water everywhere. And I could hear it. I could hear it running. I walked in. Splosh, 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 splosh. And I turned on my phone's flashlight because there was no power. And I saw that there was literally a waterfall coming through the ceiling. Well, it's a 2-story house. So I thought about running upstairs, but instead I ran downstairs. And when I got into the basement, I found 4 inches of water. 4 inches of water in the basement. It had gone from the 2nd floor into the 1st floor, through the floor, 4 inches of water. I turned the water off at the water valve. By the way, you should probably figure out as part of your adulting, it's not just about I can have beer. It's not just about I can go to the casino. It's, oh my God, when I have to go to my dad's house and turn off his water, you know how to do that. So you should really go do that. Now, what turned out was, even though my aunt left the faucets running, she didn't do anything about the shower and the bathtub. And in fact, it was water that was frozen in the shower line that burst and caused that amazing event. Well, every New Englander, every person in New York knows that, you don't want your pipes to burst, especially when you're not there. So my mom, she wants to go to bed, and she wants to know, can she go to bed, or will her pipes burst? So let's build her a differential. Let's build her the model using Newton's formula. If you like, you can derive this for practice. Remember that Newton's got temperature, the rate of change in temperature with respect to time is proportional to T minus temperature of the surroundings, T sub S. Okay, so we're going to have T sub S here. That's it. Great. And we should be able to go from here. In fact, if you identify it as T sub S, you can put that in now. And you can derive this equals K T. No, just K. No, just K. Okay. So derive that if you want. I'm going to start with the model, if that's okay. And so when I plug values into Newton's law of cooling, I know that T equals T sub S plus T sub O minus T sub S e to the minus kT. Great. We know that T sub O is 68. We know that T sub S is 10. And so I get T equals 10 plus 58 e to the minus kT. Well, Mom provided me with this extra information. She wanted to know if the temperature is 57, e to the minus k times time, 9. So I've got to solve for k and plug that k back in, and then I'll have the model. So let's solve this equation for k. Why don't you solve it, and I'll solve it, and we'll compare our k values. Okay, pause the video if you're actually working on this and don't want me to spoil it, because I'm about to reveal the k. Okay, I got a k of negative 0.0233661. And so I'm going to take this and plug it in there. Okay, T equals 10 plus 58 e to the. I solve for k. Is this negative? No, because when I divided, I took the ln. That gets me negative k. Good. So negative k is this number. So negative k is that number. Okay. So I've got negative 0.023366165 t. Great. All right. There's our model. And what does my mom want to know? My mom wants to know 7 a.m. What's the temperature going to be? Well, we know that time equals 0 is 1 p.m. So 1 p.m. to 1 a.m., 12 hours. 1 a.m. to 7 a.m., 6 hours. So 12 hours plus those 6 more hours, I got 18 hours. So I'm plugging in 18 here. Now, if this answer turns out to be below 32, Mom needs to, run the water, not just go to bed. But if this number is bigger than 32, go to bed, Mom. Don't worry about running off the faucets. So let's see what happens. I'm going to take that number times our rate. I want e raised to that power. And then I want to multiply by 58. And finally, I want to add 2. And I end up that the temperature is going to be 48.0 6 degrees. No worries, Ma. It'll be chilly, but no, your pipes aren't going to freeze. Okay? All right. Well, I think that's sufficient for us here. That's the last of these differential equations that take us down the road of exponentials and logistic curves